application of the phase rule to some simple systems. Basically, what we have to first look at is what are the variables, set of variables. The set of variables we consider largely only two phases, but the temperature pressure, let's say two phases are there, so I can consider the mole fraction vector in phase 1 and the mole fraction vector in phase 2. If you have more number of phases, then you have to consider mole fraction vectors. So these, the number of variables are C minus 1. The C is the number of components. And the equations are, of course, the equality of chemical potential. Now we convert the equality to the fugacities of the components, because typically models are proposed for the fugacities rather than the chemical potential. So, if you take, for instance, we've already considered the implication of the phase for a pure component. If you have one phase, the number of variables is 2, temperature, pressure, let's say. So, for the pure component, only temperature and pressure are the only variables that we will consider. So, we have two single phase and 2 degrees of freedom. We have two phases in coexistence, and only one of the two, temperature or pressure, can be varied. The other is automatically determined. We have three phases. It's a triple point. There is no degree of freedom at all, and so that's why the triple point for pure surface is automatically fixed, and there is no degree of freedom. Now the complications in mixtures arise because of the presence of more number of components and more number of variables that give the composition of it, specify the composition of the two phases. Now the simplest we can consider beyond pure component is the binary mixture. In a binary mixture, let's say I consider absorption of let's say carbon dioxide or ammonia, standard. So typically, both carbon dioxide and water, let's say, are present in both the phases. Right? So this would mean, for instance, I can take temperature, pressure. I have to choose one binary, so only one independent mole fraction for each phase. Right? So C minus 1 becomes 1. I need for each phase, and so this would be, I can choose this to be YCO2 for the gas phase and XCO2 for the liquid phase. So 4 variables. The equations are 2, right? So I can write this as FCO2 liquid is equal to FCO2 gas and FCO2, so FH2 liquid. So you can play this in the phase rule, once you list out, because you want to compute the phase equilibrium, you need to look at the equations as well. You can each time check whether the phase rule is actually being satisfied or not. Because without writing any of that, I can write F to be 2 minus 2 plus 2 equal to 2. So to clearly see there are 4 variables, 2 equations, so it's satisfied, right? So I have 2 degrees of freedom. For instance, one standard is to choose the temperature and pressure. So, and I can plot YCO2 versus XCO2 for instance. This is one page. So that means presentation of data, you should see whether it is consistent with the phase rule. For instance, let's say only this is given. Somebody gives you the absorption characteristics of carbon dioxide or ammonia or whatever. And then we say that at a given temperature, this is how the mole fraction in the gas phase versus the mole fraction in the liquid phase will behave. Let's say something like this. Now we know that there is some information that is not given. You have every right to ask what is the pressure at which this data is generated. Because it could happen that the absorption characteristics do not change significantly with pressure. We don't know whether that will actually be a good assumption in all cases. But clearly, somebody will just give you be the same. So once any data is given either in the form of a figure or in the form of tables of data, experimental data, you have to ask whether it is consistent with the phase rule. So that's a very important application of the phase rule. So you can get to calculating the phase equilibrium. Experimental presentation of data, you should be able to verify whether it is consistent with the phase rule. So now often an assumption is made as to simplify the presentation of the data. For instance, a very good approximation in conditions where absorption is carried out, gas absorption is carried out, is to assume that there is very little water in the gas phase. That's an approximation. So if I assume, then the simplified system would be simply CO2 in the gas phase. It's an assumption. It's often a good assumption, and it's clearly simplified as we will see. And so I have CO2 plus H2O. Now what happens to the degree of freedom? Because if you notice the way we derived the phase rule, you might not have noticed it. Right? The phase rule, common derivation of the phase rule, assumes implicitly that all components are present in all the phases. Now, if only some of the components are present in, some of the components are not present, then the question is this Fa equal to C minus? Is it valid or not? Because that assumption you have made, right? When you write mu1 in phase 1 is equal to mu1 in phase 2, automatically you are assuming that the component 1 is present in all. If you go back to the equation, the whole term, the implicit assumption is there. Otherwise, equality of continuity cannot be written for a component which is not there in a particular phase. Right? So the question is it valid? Now we will show here the general proof becomes very complicated because you have C components and pi phases. There are n number of combinations you can consider of some of the components not being present in some of the phases. But the fact is that the final equation for the degree of freedom holds whether all the components are present in all the phases or not. What will happen is that there will be a reduction in number of variables. There will also be a reduction in the number of equations. So the numbers will cancel out and the same answer you will get for the degree of freedom. So proof of this is difficult, somewhat cumbersome to give generally, but you can verify it in each and every case. Now let us say what are the sets of variables. Temperature, pressure is always there. Now we see why CO2 is not a variable. We know that since we are assuming that there is no water in the gas phase, this means that this is actually equal to 1 in this case. So there is no point in listing it as one of the variables. So you can see there is a reduction in the number of variables. So all I can write is x CO2. So only 3 variables. Now what about the equation? So the equation is that only one equation is possible because only carbon dioxide is present in the both phases. So you should know the equality of chemical potential can be written only for that component which is present in both the phases. So I can write this as F CO2 in terms of the gas. F CO2 gas is equal to liquid. So 3 variables and 1 equation. So obviously F is, this F should not be confused with this F. The degree of freedom is continuous to remain 2. But now there is a considerable simplification in the representation of data because here temperature and pressure. So if I go to another temperature and pressure, I need another block. Now you can see here, for instance, if I want to plot, typically we plot pressure versus solubility because there are, so I can fix the temperature, and so that is 1 degree of freedom. Then if I plot this, right, So then the information would be complete. So I can fix the temperature, let's say T1, and I get typically solubility increases with pressure. So I get something like this. You know, the phase rule is perfectly satisfied because you have to verify that is the phase rule satisfied. Degree of freedom is 2. 1 degree of freedom. I can choose pressure, then I get solubility, or I can choose solubility, I get the pressure. So 2 degrees of freedom completely determines the state. Really determines the state because all the variables are known for the two-phase system. So that is what we have. Now we want another temperature. So this is T1, and then I can put T2. So the entire information, the absorption characteristic, can be compressed in one plot, P versus X versus at different temperatures. Typically, the solubility decreases with increase in temperature. So what that say? What is T1 then the highest temperature, or solubility will decrease with increase in temperature? What can you say about the relative T1 greater than T2 greater than T3 or less than T2 less than T3? T1 is greater because solubility height is, for a given pressure and temperature. So for a given temperature and pressure, this is the solubility, right? Now for the same pressure, the solubility is going to decrease with increase in temperature. Now it is increasing. So that means that T1 is greater than T2 greater than T3. Some anomalous cases are there where the solubility can actually increase with increase in temperature. Typical behavior, you see, get a good reference that you should consult. Good references for phase diagrams are not necessarily thermodynamics textbooks, but mass transfer textbooks, and particularly you look at Raoult. He has such a good collection of phase diagrams, various systems. Absorption is one of them. Cedar and Henry also is a good source. Maybe many others. But he doesn't discuss really detailed application of the phase rule, which is what they will add to those diagrams. So this is the way of representing. Now when it comes to, you can clearly see, even though the number of degrees of freedom is the same, you can ask what is the simplification. Simplification is not in the number of degrees of freedom, but the fact that there are few number of variables makes the representation easier, and also the calculation of the phase equilibrium easier, because here I have to choose only deal with only one equation, because here I have to deal with two equations. This assumption, so you have to always look whether an assumption can be made which will simplify the solution or even representation. Right? So this is one example where it does. Another very famous example for typically for two-component binary system, which we can say here binary, but only this is a general case. This is only one component distribute between the two phases. So before we go to distillation, we are considering some simpler cases. Distillation binary, typically both components are present in both the phases. That's obviously a level of complication, which is what I presented. Typically in absorption, it's a good approximation to assume that one of the components is not present in the one of the phases. So it makes the calculation simpler. Now what can we say about, let's take the simpler case. What can we now say about the models that are commonly used in absorption? So what is usually done in this case is that the gas phase, because the pressures in absorption are typically very low, right? So typical cases are low. So because that's the next step. How are we working? This can be determined experimentally. But if we were to calculate the phase diagram, that is what we come to the next step. We need models for the chemical potential of the gas phase. Typical model is assume the gas phase to be an ideal gas. Pressures in absorption are typically at fairly low pressures. So you have to understand that the books present models for gas absorption, you have to know they make an approximation about the phases. Now here, if you look at this, the vivacity of the liquid itself, right, it's clearly a function of temperature and pressure. Both, in fact, both are actually the vivacity of the carbon dioxide, right? That is a pure component only. So it can be only a function of temperature and pressure. Because we are making that approximation that the gas phase is a pure component, has only carbon dioxide. This, of course, will be a function of temperature, pressure as well. It is a mixture actually. The three variables, two components, temperature, pressure, and one of the mole fraction. So now by making this approximation, I have removed the temperature dependence. If you assume that the gas phase is behaving like an ideal gas, and I simply replace the vivacity by the pressure. Partial pressure, if it were a mixture, right? Since this is only a pure component, I can replace it by pressure. So considerable simplification results. Otherwise, this could be a function of both temperature and pressure. You have to calculate the vivacity using the equation of state. And here, typically what the Henry's law is used, where you replace this by a function of temperature, although the Henry's law concept will obviously be a function of temperature and pressure, even if it is so. And then you write this as XeO2. This is the Henry's law. So what again we are making an assumption, right? We are saying that the vivacity of the liquid phase of carbon dioxide is proportional to the mole fraction. Means this is valid only for dilute solutions. For dilute solutions, this will be a good approximation. Now the proportionality factor, because we see here both temperature and pressure are there. So strictly, this would be a function of temperature and pressure. But we are saying the liquid phase pressure effects are negligible. So typically, what is plotted as a Henry's law constant, right? It's actually not a constant, it's a function of both temperature and pressure, right? And we neglect the pressure dependence. So typically, it will be only a function of temperature, right? So we can now clearly see. So if the H of T is given, the Henry's law, you see that in Henry forces has a diagram which gives the water absorption of various gases in water. It gives the dependence, the plot of H versus T. Or you can plot 1 over H or something. So he has given that. So you can then go ahead and calculate the phase diagram itself. This is given, right? So at a given temperature, it's a constant. It's a linear actually. Right? So you can calculate that. But that will be valid only for low mole fractions. Won't be valid for the higher ranges of the absorption. So that's one model that is used. And now the other famous example, which I will regard as a complement of this. So this we won't consider for now. So looking at only one component distributing. Another that is famous is humidification. Now the humidification will get another computation and another assumption is implicitly made in humidification, and that has to do with the way we treat air as a single component. So humidification basically deals with air-water mixtures. Air is brought into contact with water and it gets humidified. Okay? So at equilibrium, I have air. This is now air plus water in the gas phase, and only water in the, again an assumption is made. Typically you will have air and water, but we assume that under conditions where humidification experiments are carried out, air doesn't absorb into water, and so we can regard the water, the liquid phase, to be effectively pure water. So the air is a mixture of nitrogen and oxygen and various gases. Predominantly nitrogen and oxygen, neither of them actually absorb in water at ordinary conditions. So that's a good approach. That's what is made in humidification. Whether you agree with it or not, that's the implicit assumption that's made. But this is different. Here the liquid phase is binary and there the gas phase is binary. On top of it, you can ask, since we know that air is a mixture, even if you restrict and say that air is a mixture of only two gases, right? Typically the way this is done is to treat this as a single component. So when we apply the phase rule, right, how does the phase rule is the same? Two components, two phases, so F is equal to 2. Now what are the variables? Temperature, pressure, right, and Y, water in the gas phase, so I am calling it as Y. That's all. The liquid is pure. Now obviously, if I were to really consider air as a mixture of N2 and O2, again Y N2 also I have to include one more, either Y oxygen or Y nitrogen, mole fraction of either nitrogen, has to be included as one of the variables. Right? So now the equation of course are volume 1, the FW of liquid is the water. The only equation, because water is the only component that is present. So why is it that we can, so is this correct? Which is correct? Whether I should take Y nitrogen or simply take only one. Treat air as a single component. Because if I treat nitrogen and oxygen as two different components, then I am going to get a different answer for the degree of freedom. But typically that is not done. So what can be a justification for that? They are always together. The ratio of Y N2 to Y, because you have another equation here that Y N2 by Y O2 is, let's say, typically it's taken as 79 by 21. So you effectively, even though you have two variables, you have another equation. Actually, you know, I have to take that point. You can say now I will introduce another variable, but it's not strictly. So let's stick to this. Let's stick to this. But I have to take into account this. The crucial, there is a link between our assumption that air does not dissolve in water. Okay? So nitrogen and oxygen, if they were to allow to dissolve in water, then they will both obviously dissolve to different extents, and you can't discard, treat them as one component. But here, you put some air in, nitrogen and oxygen are going to remain together and in the same ratio. Effectively, even though I have two variables here, I have to consider this equation. Now you can argue that I have introduced another mole fraction, but clearly I can write this as Y N2, where 1 minus Y N2 minus Y W is equal to 79 by 21. So even though I have this variable, I also have an additional equation that relates the mole fractions, right? So I start with this YW and YN2, but I have this. So instead of adding that, I simply assume that air is present together, and so I will, rather than adding this equation, I will simply reduce the number of components to 2 only. That's what anyway is typically done. This can be a justification for doing that. The crucial point here is that there is neither nitrogen nor oxygen in the water. So then only this relation is satisfied with the gas phase. In both of them, let's say conditions are set very high pressures or something, where both nitrogen and oxygen can dissolve in water, then the whole problem becomes completely different. So then they won't, each one will absorb differently in water or dissolve differently in water. So when they put a mixture of nitrogen and oxygen, the ratio 79 to 21 and allow them to come to equilibrium, right? They will obviously, you cannot expect that after the equilibrium is reached, the mole fraction of nitrogen and oxygen will continue to remain 79 by 21. There you have to consider them as two components. But because we are assuming conditions where neither nitrogen nor oxygen dissolve to water to an appreciable extent, so I will simply not consider this additional complication and treat air as a single component. But you can physically see they are going to be together, as you said. Right? So this is what we will consider. Now here, variables we have written. Now if you see the liquid, it's a pure component, and the vapor is clearly a function of temperature, pressure, and so again three equations. Now in one equation, three variables. Degree of freedom is 2. So now what the model that is done, model that is adopted is assume the gas phase is an ideal gas mixture. If we find humidification at 1 atmosphere only, maybe slightly higher pressures, but it would still be an ideal gas mixture. So what would you replace this by? What is the fugacity of the water vapor in the mixture? What is fugacity of any component in the mixture equal to for an ideal gas mixture? The partial pressure. So this would become PYW, and this is usually silently replaced as PW saturation, and the pressure dependence is ignored. It will not only ignore the pressure dependence, but you replace the liquid fugacity by the saturation, the liquid fugacity of water. This is a pure component, because it is pure water only. Its fugacity at the given temperature and pressure is simply replaced by the saturation pressure. So how is this justified? What are the approximations involved in this? Because water is a liquid, right? Let's say given a particular temperature, right? And let me consider the pressure volume diagram. So when given, let's say room temperature 1 atmosphere and let's say 30 degrees centigrade, where do you think the state of that water would be on this diagram? Is it going to be on this segment or this segment or this segment? Top, horizontal, or the bottom segment? Horizontal. This is a pure liquid, and it's not boiling or anything. 1 atmosphere, 30 degrees centigrade, it's a pure liquid. So where is it going to be? The top section. It's going to be somewhere here. So this is the fugacity that we want. But what the books say is that you replace this by the saturation pressure. This is all water, pure component. The liquid is a pure component. At that temperature, T1, let's say. So what approximations are you doing? Now can you tell me? I'm replacing it first by the saturation. Replacing it, so you have to consider it as 2 stages. Let us say I replace it by the saturation fugacity. Right? So first approximation, FW. Let's say this is P1. So what am I neglecting there? If I am replacing it by the saturation fugacity. What factor? We introduce some factor, correction factor for fugacity. No, not gamma. Yes, what factor are we neglecting? The so-called pointing correction factor. The way you have forgotten that. Use it recently. We said the pointing correction factor corrects the fugacity of a subcooled liquid, right? With respect to the saturation, so pointing factor times saturation fugacity. We also showed how to calculate the pointing factor dependent on the volumetric data of the liquid, right? And this is exponential, it's the exponential of something, right? Some integral. So if that becomes, so this is what it is, so the pointing, this is the exact. That's basically what we see, the pointing factor is actually equal to 1. Now you tell me, further if I want to approximate this, to PW sand, what is the approximation that is involved there? Velocity coefficient is 1, so what does it say about rate? It is like behaving, yeah, you can say sufficiently low pressure. Right? It's not quite, we are not actually approximating the liquid by an ideal gas, but sufficiently low pressures, then the fugacity, saturation fugacity can be replaced by the corresponding pressure, which is the saturation pressure. So that is what we are doing, right? So you should not think, this is an approximation. First of all, you have to understand that so many books give the humidification equation as if it's some law of thermodynamics. It is not. There are so many approximations involved, which are perfectly valid. But you should know how to interpret these equations from a thermodynamic point of view. So we coming to solving this somewhat complicated equation, to solving this, we will just split the temperature depend. This now is a function of temperature pressure. We made it as a function of temperature alone. So effectively, it is low pressure. At low pressure, fugacity can be replaced by the saturation pressure. This cannot correspond to very high, temperatures. So the pressures will also be high. Right? So this might be approximate for low pressure. This is 1 atmosphere or a few atmospheres. It is where humidification takes place. That can be really considered as sufficiently low pressure that we are neglecting the fugacity coefficient, as you said. And so that's what we are doing. So this is the equation anyway that is adopted. We are looking into the what is behind these equations. Go to any book on humidification, mass transfer book. This is the equation that they will give. So this is what we are assuming. Now, the plotting of that typically, the humidification also has an additional complication in the sense that first there are many new variables of composition that are introduced. For instance, what is introduced here is what is typically introduced is absolute humidity. So you should be aware of the various other measures of composition that are used. Now, absolute humidity can be either mass based or mole based. We will write the expression for mole based. Absolute humidity is simply the mole ratio YW by YA. So mole ratio. So now for a binary mixture, the absolute humidity, molar absolute humidity, since the gas is a mixture with just two components, and we're treating air as a single component, so it's clearly 1 minus. It's somewhat different from the mole fraction. The sufficiently low values of the mole fraction will be almost the same, but you have to know the distribution. But more important than this is the fact that, suppose let's say I were to plot this. We have to introduce another. This saturation is different from this saturation. This is another side, maybe I can put it here. Because let's say how it will look when we plot it. Let's say we plot it at a particular temperature. So let's say I choose the temperature T1. Right? Now I typically it is plotted like this, I guess. T versus particular pressure, and you have T versus Y double S. So pressure is fixed, so I can take it over here. YWS is PW sand by P. So P is fixed, let's say P1. So what do you think the curve will look like? Saturation pressure, does it increase with temperature or decrease with temperature? Saturation pressure, does it increase or decrease? Huh? Increase typically. You see the coexistence curve so many times, right? So what do you expect the plot to look like? Going to look like this or like this? First one or second one? First option or second option? This is the first option. One or two? Two. Oh. You just said that the saturation pressure will increase with temperature. As temperature increases, what would happen to YWS? It will also increase. Right? So you have to be very careful about these. These are very simple common sense ideas and do not get bogged down in the complication of stochasticity and all and forget these to make these equivalent. So what I'm trying to point out is you can very quickly plot how this is going to look like. But what happens in humidification is that the typical humidification operations involve air-water mixtures which are actually not in equilibrium. So that is why you have two important measures of deviation from the saturation. So this is maybe what would be called as 100% saturation. So we need so many other curves. So there are two important measures. One is the relative humidity. Sometimes expressed as percent or sometimes expressed as fraction, typically less than 1 relative humidity, or the percent saturation. Both are slightly different. Now the relative humidity, let's say this is now regarded as 100% saturation. Let's say the relative humidity is 70%, right? Relative humidity is, humidity refers to amount of water in the air-water mixture. Relative humidity 70% means then YW actual is 0.7 times YWS. This is relative humidity equal to 0.7 or 70%, whichever you want. So now where will the curve of 70% humidity, where is it now you can clarify? Do you think the 70% humidity is going to lie like this or like above or below? Below, right? Very clearly. Because this is the maximum at a given temperature. 70%, let's say I can plot, this is YWS. At that pressure and temperature, 70% of that 0.7 would be here. And I can plot the 70% curve. So you can plot the whole range of curves very easily. The entire range. 70%, 50%, 40%, 30%, so on. They will all lie like that. Now the percent saturation, some might be different in terminology. I think I am following what Raoult has given. The percent saturation has to do with the mole ratio. We will now call this capital YW. So once I have YWX, that is a saturation. So you have to remember that typically YW, I can write this as actual YW. If I want to generate, it would be sometimes I can maybe call this alpha, the relative humidity. It's a factor, right? It's a fraction times PW sat by P. So the PW sat by P is the saturation, and if we multiply it by 0.7 and 0.8, I think we get 70% relative saturation and 80% relative saturation and so on. Now, the percent saturation has to be with how much the mole ratio is different from the saturation. So once I get the saturation, I can easily calculate YWS, which I will get by simply taking YWS by 1 minus YWS. Now if I put fraction, I will call that maybe alpha percent saturation, PCS or whatever. So that is alpha, will give me the actual YW. So YW would be alpha, let's call it PS times YWS. So the two will be somewhat different because the mole ratio is not exactly equal to the mole fraction. So if you are looking at saturation suppose now I can plot capital YWS. This is let's say T1. If I can plot small YWS, just the mole fraction, I can easily plot the saturation. So I get a curve which is somewhat similar. Right? So this is 100% saturation, YWS. Now in this, if I mark off 70%, 80% and so on, I get what are known as percent saturation, which is somewhat different from relative. You will find the relation between the two. Maybe I can give a simple numerical example to illustrate that. But the two are slightly different. So the percent saturation factor, right, is if I say 80% saturation, right, that means what I have to do to find the actual, suppose let's say the what is the mole fraction of water vapor in the air-water mixture, which is that I can consider two possibilities. One is 80% relative humidity and another is 80% saturation. It's called percent saturation. Right? So this would mean that YW, the actual, is 0.8 times YWS, the mole fraction. This would mean that capital YW is equal to 0.8 times capital YWS. You can easily figure out now for 80% relative humidity what would be the percent saturation and vice versa. The two will not exactly match except at 100%. It is very important to know that when you come to humidification, the paper gives a lot of examples to understand this. When you come to humidification, you also have to deal with this is strictly maybe within our part of equilibrium thermodynamics. But you have to be aware of this. This is what the relative saturation or relative humidity means. And so this is what we have. So there is an important quantity called the dew point. Right? So what, let us say now, the dew point is a mechanism, it illustrates a mechanism to bring a mixture which is subsaturated to the saturation points. So let's now take, let's say 60%, we can say. Let's say something is like 60% saturation. So now I have a mixture which is here. That means it's at a particular pressure and at a particular temperature, and it obviously has 0.6 times YWS corresponding to that. Now, what Raoult points out is that if you cool this mixture away from any water, so you're cooling it at constant humidity. That is how you reach the dew point associated with the mixture. So cooling out of contact with water, that's what he says. Out of contact with water means you are just cooling the mixture and not allowing it to further equilibrate with the mixture. See, one way of making this saturated is simply add more water and you will get 100% at that temperature. Now this is somewhat different. You are cooling it. You say that I want to retain the amount of water vapor, the relative amount of water vapor in the mixture, but I want to bring it to saturation. One way of doing it at fixed pressure is to reduce the temperature. So when you reduce the temperature, you then hit the saturation curve, but at a different temperature, so the mixture now becomes completely saturated. It's now a saturated mixture. So there's a big difference between the state here and the state here. The difference is in the temperature. Pressure is the same, mole fraction is the same. But by reducing the temperature, we bring and make the mixture saturated. And Raoult points out further, if you continue to cool the mixture, then what would happen? It will be under equilibrium, right? You continue to cool the mixture, then what will happen, he says, is that it will go along this curve. That means the mole fraction of the water vapor is decreasing. That means the liquid is condensing out of the vapor and coming out, and you are having a progressive retaining the saturation nature of the mixture. You have actually reduced the water content of the air-water mixture, and so you are reducing the temperature further. This is what will happen with continuous cooling. So humidification is very important, and also because it has this additional complication of us having to deal with a non-equilibrated mixture. So you have to know how to measure that, how to get the measure and various phenomena associated with it. Same thing can be done. I will get you to read up from Raoult. Same thing can be done if you are now looking at the plot of temperature versus, mole fraction versus pressure at a fixed temperature. You can see now how it will look like, right? Mole fraction versus pressure at a fixed temperature. Clearly, this is an inverse relation. Now, the mole fraction will decrease with the increase in pressure. So, you can do the same phenomenon. The new pressure can be calculated. You might have to increase the pressure to bring it to saturation. So, you can see how this would look like. The plot of this would look like. I think what I am saying is that fixed temperature. Let's say, fixed temperature at T1. Now, plot YWS versus P. Clearly, it is somewhat like a hyperbola, so it is going to look like this. This would now be again at 100% saturation. Right? So this is what we get in inverse, because this is fixed, temperature is fixed, so that saturation pressure is fixed for that temperature. Y versus P, 1 over P is going to look like this. Right? So now it's like, now you can again calculate various the relative saturation, 70%, 60%, and so on. They will all obviously again lie below this curve. And again you can, let's say I consider a 60% saturation. So a mixture is there at 60% saturation. Now if I want to bring it to saturation, clearly I have to increase the pressure and further keep increasing the pressure. So either, just as we do for normal pure component boiling, I can either heat the water at 1 atmospheric pressure, right, up to 100 degrees centigrade, or if I want to do the boiling at 1 atmosphere, I have to heat it to 100 degrees. So, or if I want to boil it at the room temperature, I obviously would have to increase the pressure, decrease the pressure, right, to make it boil, right. So the two phenomena are complementary to each other. Are there any questions? If not, we'll continue this in the